Hi, and welcome back to Codex. Today's speaker is Matyas Domokos from the Alfred Rainey Institute of Math. Professor Domokos is an expert in algebraic invariant theory. Today, he will tell us about degree bounds for separating invariants. Take it away, Matyas.
Thank you very much. Thanks for the introduction and for the invitation to speak here. So first, the plan of my talk. First, I would like to review some basic facts about generating sets in invariant theory. And then we will recall the notion of separating invariants and mention some trends in the study of separating invariants. So first, some general good properties which typically hold for generating sets under some assumptions that the field is nice or the group is nice, but for separating invariants, they hold without any conditions. And we would like to mention some results where separating invariants are used to state strengthened versions of classical theorems. So for example, you have some property which generating sets rarely have, and then a strengthening can say that you have the same property only in the same situations, even if you relax the condition for generating set to separating sets. And then I will turn to the topic of degree bounds and compare degree bounds for separating sets with degree bounds for generating sets, which is interesting even in the classical situation of reductive groups over the field of complex numbers. And if time permits, I will mention some examples of explicit separating systems from the literature. So the basic setup of invariants here is the following. So G will stand for a group for all the talk, F for a base field, and V for an n-dimensional vector space over F. And suppose that we are given a representation of the group G on the vector space V, or frequently simply G will be a subgroup of the general linear group GLV. And I will use the phrase that I will say that V is a representation of G. And denote by FV the algebra of polynomial functions on V. So this is just the n-variable polynomial algebra. So we can think of the indeterminate xi as the function which maps a vector to its ith coordinate. And FVG stands for the set of those polynomial functions which are constant along the G orbits. And this is called the algebra of G invariant polynomial functions on V, because this is clearly a subalgebra of the polynomial algebra. Of course, when the field is finite, then identifying polynomials with functions is not correct, but basically the action of G on V induces an action on the polynomial algebra via linear substitutions of the variables. This is an alternative way, more algebraic way to think of it, by graded F-algebra automorphisms. And the algebra of invariance is just the fixed point set subset for this action of G. And the general aim of invariant theory is describe the algebra of invariance, for example, find its generators, or try to determine the relations between the generators, or find some structural properties of the algebra of invariance, or compute the dimensions of the homogeneous components of the algebra of invariance. Let's refer a star for the assumption that G acts on the polynomial algebra completely reducibly. So observe that the action of G preserves the homogeneous components of the polynomial algebra. So the polynomial algebra is the direct sum of finite dimensional G invariant subspaces, and complete reducibility means that every homogeneous component is the direct, decomposes as the direct sum of irreducible G representations. So under these assumptions, it turns out that some homogeneous invariants generate the algebra of invariants as an F algebra, if and only if they generate the ideal in the full polynomial algebra, which is generated by all the homogeneous invariants of positive degree. So this is called the Hilbert ideal. So in the full polynomial algebra, we take the ideal generated by all homogeneous invariants of positive degree. This is the Hilbert ideal. And a lemma is that some invariants generate the Hilbert ideal as an ideal, if and only if they generate the algebra of invariants as an algebra. So consequently, the assumption star implies that the algebra of invariants is finitely generated as an F algebra by the Hilbert basis theorem. So in fact, this was the very reason Hilbert proved the Hilbert basis theorem. As an example, the assumption star holds for finite groups when the characteristic of the base field does not divide the group order. And in this case, we know even more. In this case, we even know that the algebra of invariants is generated by elements whose degree does not exceed the group order. So in characteristic 0, this is a classical theorem of Noether, which was extended to the full non-modular case more recently by Fleischmann and independently Fogarty. So Hilbert's 14th problem asked if the algebra of polynomial invariants is always finitely generated. And Nagata gave the first counterexample, so found a 32-dimensional complex representation of the vector group, the direct sum of 13 copies of the additive group of the field of complex numbers, such that the corresponding algebra of invariants is not finitely generated. And this example was simplified and better understood later by other people. And this study is culminated in the theorem of Totaro, showing that, in fact, for any field F, there exists an 18-dimensional representation of the vector group F cube, such that the corresponding algebra of invariants is not finitely generated. For comparison, I mentioned the theorem of Weizenbuch, that if we take just the additive group of the complex number, for any finite dimensional representation, the corresponding algebra is finitely generated.
So I got a question. If the vector group is instead of cubed or to the 1, if it were squared, is it known whether?
I think it's not known.
Okay. Awesome. Thanks.
So a comment on the group. If we fix some subgroup of the general linear group and some polynomial, so the assumption that the polynomial is G invariant, this holds if and only if it's invariant with respect to the Zariski closure G bar of the group G. So GLV is just the group of n by n invertible matrices over F. So it's a linear algebraic group, so it makes sense to speak about the Zariski closure of a subgroup. So therefore, because of this assumption, it's not really a loss of generality always to assume that we are working with a linear algebraic group G, which acts on V via a so-called polynomial representation, meaning that the matrix elements of the representation are polynomial functions on the group. And sometimes we a slightly more general setup is when X is an affine variety. For example, F can be V, the affine space, but the action is not necessarily via linear transformations, but we just require that the action map from G cross X to X is a morphism of algebraic varieties. In the class of linear algebraic groups, an important subclass of is formed by the so-called reductive groups. and invariant theory of reductive groups is particularly well developed and nice. So the definition is that, so when I speak about a reductive group, I will always assume that that the base field is algebraically closed, and a group is called reductive if the connective component of the identity has no non-trivial unipotent normal subgroups. So for example, the so-called classical groups, the general linear group, the special linear group, the orthogonal group, and so on, and the direct products of such groups, they are all reductive. And another important feature is that compact real Lie groups can be obtained as a maximal compact subgroup of a complex reductive group. And at least in characteristic 0, reductive groups have the property that all their finite dimensional representations are completely reducible. So as we mentioned before, it turns out that the algebra of polynomial invariance is always finitely generated. In characteristic P, complete reducibility of representations of reductive groups in general does not hold, only for very special reductive groups, but Nagata found a weaker assumption which still guarantees finite generation of the algebra of polynomial invariance, and Haboush proved that all reductive groups have this property. So suppose now that G is a reductive group and take some generators of the algebra of invariance, then we can form the polynomial map from the vector space V into the affine space F to the M, whose coordinate functions are the generators of the algebra of invariance. And it turns out that the image of this map in F to the M is a Zariski closed subset. So it's not just a so-called constructible subset as the image in general of an affine variety in algebraic geometry is a so-called constructible subset, but here it's even Zariski closed. And we shall use this the notation V over G for this subset. And this V over G is not an orbit space, but it's a so-called categorical quotient in the sense that any G invariant polynomial map from our vector space to somewhere factors through this map H. And moreover, 2 points in the vector space are mapped to the same, have the same image on their H, if and only if the Zariski closures of their orbit intersect non-trivially. And moreover, the Zariski closure of an orbit always contains a unique closed orbit. So therefore, the points of V over G are in bijection with the set of Zariski closed G orbits in V. So V over G, this space parameterizes closed G orbits. So as a well-known example, let's consider the group of GLNC acting by conjugation on M by M matrices. Then the corresponding algebra of invariance is generated by the coefficients of the characteristic polynomial. So this affine quotient map sends a matrix to the assigns to a matrix the collection of the coefficients of its characteristic polynomial. So basically it determines the image under this affine quotient determines the set of eigenvalues of the matrix. But as we know, if there are multiple eigenvalues, different matrices without being in the same orbit can have the same set of eigenvalues. So this is not an orbit space. And now the definition of a separating set of polynomial invariants is the following. So probably it was always in the back of mind of people working in invariant theory, but It was formulated first, as far as I know, in the book by Derksen and Kemper on computational invariant theory. So we call a set of polynomial invariants separating if whenever 2 points in V can be separated by some polynomial invariant, then we can find an invariant in the set U which separates them. So as we saw, I mean, so maybe the term separating set would suggest that a set of invariants is separating if it separates different orbits, but we cannot expect the existence of such set of polynomial invariants in general. And the best we can hope for is what is given by this definition. So whenever 2 points can be separated by polynomial invariants, then they can be separated from our chosen set of invariants. If that holds, then we call this set of invariants separating. So as we mentioned before, for reductive groups, this has a geometric character. We know when we have this geometric characterization that U is a separating set if and only if for any 2 points with Zariski closed G orbits, there exists an invariant in U which takes different values on them. So a set is separating if a set of invariants is separating if it can separate Zariski closed G orbits. But in particular, when G is finite, then different orbits can be separated by some polynomial invariants. So one of the good properties that, unlike in the case of generating invariants, where we have Nagata's example of a representation with an algebra of invariants which is not finitely generated, the algebra of invariants always has a finite separating subset. And I gave here the proof is easy. It just boils down to the Hilbert basis theorem again. So take V cross V and take the ideal. So we note the coordinate functions on the first copy of V by x's, on the second copy by y's, and take the set of elements, polynomials on V cross V of the form f of x minus f of y, where f ranges over all invariants. And this ideal is generated by a finite subset. And it's quite easy to see that if we take such a finite subset, we get a finite set of invariants, and they will form a separating set. But in fact, by basic algebraic geometry, one can show that if we have an n-dimensional representation, there always exists a separating set of size at most 2n plus 1. So here is an easy example that one cannot have a similarly small, expect the existence of a similarly small generating set of invariants. So we take just the 2-element group acting on the n-variable polynomial algebra by sending each of the variables to its opposite. Then the algebra of invariants is the set of polynomials, all of whose monomials have even degree. So it's generated by the quadratic monomials, and there are n times n plus 1/2 such quadratic monomials, and this is the minimal number of generators of the algebra of invariants. So it's this is So Friedenburg gave an example related to Nagata's example of an action of the additive group of complex number on the affine space, on the 5-dimensional affine space, with an algebra of invariants which is not finitely generated. So be aware that this is not, so G does not act via linear transformations. As we mentioned, Weizenbuch's theorem says that if we have a linear representation, then the corresponding algebra of invariance is always finitely generated for this group. Dufresne and Coase found 6 explicit invariants which form a separating set. So this is an example of an algebra of invariants which is not finitely generated, but where we know an explicit finite separating set. Another good feature of separating invariants that Noether's degree bound holds for all finite groups. So we even in the modular case, you don't need to assume that the characteristic of the base field does not hold the group order. For generators, so if the characteristic divides the order of the group, then the degree bound for the generators of the algebra of invariants can be arbitrarily large. In fact, a theorem of this direction is due to Richman, which says that if the characteristic of the base field divide the group order G, where G is a subgroup of GLV, then there exists some positive number alpha depending only on the group order and the characteristic, such that if we take the direct sum of k copies of the representation V, the corresponding algebra of invariants cannot be generated in degree smaller than alpha times k. So as k tends to infinity, then the degree bound for the generators also tends to infinity. So this is the situation for generators in modular invariant theory. However, a separating set always exists in degree at most the group order. So this is related to the technique of polarization. So I don't want to define polarization exactly, just a consequence on degree bounds. So in characteristic 0, if we have several copies of the representation V, to hit the degree bound for the generators, it's sufficient to take at most as many copies of V as the dimension of the vector space V. But Richman's result implies that this fails in characteristic P, in positive characteristics. However, for separating invariants, it holds in all characteristics. So I introduced this notation. So let's call beta of FBG the minimal positive integer D, such that the algebra of invariance is generated by elements of degree at most D. And beta sep stands for the corresponding number for separating sets. So this theorem for separating invariants is a consequence of a result of Draaisma, Kemper, and Wielau. And in the case when G is finite, and Grosshans also has a result which Grosshans' paper does not mention separating invariants, but implies this. inequality. And in the paper of Draisma, Kemper, and Velau, they show also that when G is finite, then instead of the dimension of V, it's sufficient to take one copy of V. If we know the separating degree bound for one copy of V, then it will not be bigger if we take an arbitrary number of copies of V. And finally, sometimes we are interested in some G-stable subvariety of some vector space V. And we are interested in G-invariant polynomial functions on this G-stable subvariety. And technically, polynomial algebra is nice. So natural strategy is to describe polynomial invariants on V and use the restriction homomorphism from the polynomial functions on V to polynomial functions on X. And we hope that the image that all invariants on the subvariety X come from invariants on V. Yeah. And if the action is completely reducible on the polynomial ring, then we do have this property. So in characteristic 0 for reductive groups, this is fine, but in positive characteristic, the proving surjectivity of the restriction homomorphism for invariants is challenging, and it can be proved in very special situations, typically using some heavy technical machinery. As opposed to that, for separating invariants, we do have it. So the restriction, a separating set on the vector space is mapped onto a separating set on the any G-stable subvariety of the vector space, at least for reductive groups. Now, a strengthened version of a classical theorem. So a very nice classical theorem in the invariant theory of finite groups, say over the complex field, is that the algebra of invariance is generated by algebraically independent elements. This happens if and only if the group is a so-called pseudo-reflection group or complex reflection group, meaning that G is generated by elements fixing pointwise a hyperplane and having a finite order. And Dufresne strengthened this theorem by showing that for a finite subgroup of GLV, the corresponding algebra of invariance has a separating set consisting of algebraically independent elements only if G is generated by complex reflections. So unless you have a complex reflection groups, it's not just that you don't have algebraically independent generating set for the algebra of invariance, you don't even have an algebraically independent separating set. A result of somewhat similar flavor about the Cohen-Macaulay property. So in the non-modular case, so if the characteristic is 0 or it does not divide the group order, then the algebra of invariance of finite group is a so-called Cohen-Macaulay algebra. So this just means that we can find an algebraically independent invariance such that the full algebra of invariance is a finitely generated free module over the subalgebra generated by these n so-called primary invariants. But this again, it fails in the modular case, as was proved by Kemper. So in fact, any group G in the non-modular case has a representation such that the corresponding algebra of invariance is not Cohen-Macaulay. And this was strengthened by Dufresne, Elmer, and Coase by showing that in the modular case, for any subgroup of GLV, any finite subgroup for GLV, if we take the direct sum of k copies of V for k sufficiently large, then the algebra of invariance has no Cohen-Macaulay separating subalgebra. So not just that the full algebra of invariance is not Cohen-Macaulay, but it cannot even have a Cohen-Macaulay separating subalgebra. Now, let's turn to degree bounds. So here we can return to the classical case when the base field is C, and I shall mainly focus on finite groups, but not exclusively. So we have this obvious inequality that the separating degree bound is at most the degree bound for invariance. Yeah, because a generating set is always a separating set. So because of Noether's theorem, it makes sense to make the following definition: to fix the group G and denote by beta of G the maximum of the numbers beta of CVG, where V ranges over all finite dimensional representations of G. So this is the maximum because all these numbers are bounded by the group order. And similarly, we define beta sep G by using beta sep here. So it's a universal bound, degree bound for separating invariants. So let's take a finite abelian group. So it decomposes the direct sum of cyclic groups of order n1, assumed to be at least 2, dividing n2, and so on. And denote by d star of G the sum of ni minus 1. And I proved that for an abelian group as above, we have that this beta sep of G is always at most d star of G, except when a group has many summands of the form C2, when beta sep of G is equals 1 plus d star of G. So typically, unless there are many summands of the form C2, the separating degree bound for an abelian group is at most this explicitly given number in terms of the invariance of the structural invariance of the finite abelian group. And as a corollary of that, we typically have that the separating degree bound for a finite abelian group is strictly smaller than the degree bound for the universal degree bound for generating invariance. So why is this corollary? So I need to recall the relation to the so-called Davenport constant, which comes from additive combinatorics. So for a finite abelian group G, the Davenport constant d of G is defined as the maximal length of an irreducible zero-sum sequence over G. So by a sequence over G, we just mean a sequence of elements where repetition is allowed and the order is disregarded. And we call it a zero-sum sequence if the sum of the elements in the sequence gives 0. And this is called irreducible if it cannot be split as the union of two zero-sum sequences. And the maximum, and it turns out that for a finite abelian group in beta of G, so the Noether number, is the same as the Davenport constant. And if we look at the Davenport constant, an easy construction shows that the Davenport constant is always greater than or equal than this d star of G plus 1. So this quantity introduced before. And in fact, sometimes we have equality here for abelian P groups or for rank 2 abelian groups. We have equality here. So the Davenport constant is just this d star of G plus 1. And in fact, some long-standing open questions in additive combinatorics, whether this equality holds for rank 3 abelian groups or for direct sums of cyclic groups of the same order. So why rank 3? Because there are already many examples of abelian groups where the inequality here is strict. So the Davenport constant is strictly bigger than d star of g plus 1. There are such known examples of rank 4 groups and higher rank abelian groups, but so far nobody found the rank 3 counterexample, but there's no proof that for rank 3 you would have equality here. Now, what about the separating Noether number? So Barna Scheffler, who is my PhD student, recently was able to determine the exact value of beta sep of an abelian group, which is the direct sum of cyclic groups of the same order. So this is a bit surprising because the Davenport constant or the Noether number, so beta, is not known for such groups. But it turns out that the separating Noether number is given by this nice formula. So if we take an odd number of the direct sum of an odd number of copies of the cyclic group Cn, say 2s minus 1 copies, then the separating Noether number is n times s. And if we take an even number of copies, so there's a typo here. So we take 2s, the direct sum of 2s copies of the cyclic group of order n, then beta sep is n times s plus n over p, where p is the minimal prime divisor of n. Barna Scheffler was also able to compute beta sep for rank 2 abelian groups. So this is a class of abelian groups where beta equivalently the Davenport constant is also known. But again, the formula for separating Noether number is different and strictly smaller unless n equals 2. And I mention an infinite sequence of non-abelian groups for which the separating Noether number is known. So Kalman Tsister proved that if we take the non-abelian semi-direct product of a cyclic group of order P for a prime pre and the 3-element group, then the Noether number is P plus 2, whereas the separating Noether number is 1 less, it's P plus 1. And in fact, the exact value of the Noether number is known only for a very limited number of groups, which is not a surprise because we saw that even for abelian groups, computing it is equivalent to computing the Davenport constant, which for which the exact formula in general is not known despite of many efforts. But with Kalman Tsister, we were able to compute the Noether number for all non-cyclic groups with a cyclic subgroup of index 2. And it turned out that it's usually 1/2 the group order plus 1, except for the so-called dicyclic groups when it's 1/2 of the group order plus 2. So the smallest dicyclic group is the quaternion group of order 8. And recently, together with Scheffler, we proved that this is the same. The separating Noether number is the same. In the study of separating invariants, I found the notion of Helly dimension very useful. So this definition was introduced first in a paper of mine for finite groups, and later in a paper together with Endre Szabó, we extended the definition for linear algebraic groups. So for a linear algebraic group G, we define the Helly dimension kappa of G as the minimal positive integer k such that if we have a set of cosets in G with empty intersection, then it is possible to select at most k cosets from the set which already have empty intersection. So this we named Helly dimension because of this, the analogy with Helly's theorem in convex geometry. And it turns out that for a finite abelian group G, the Helly dimension is just the rank, the number of generators plus 1. And also, for a linear algebraic group over a field of characteristics 0, the Helly dimension is always finite. So what's the relevance of the Helly dimension for separating invariants? So suppose that our representation V decomposes as a direct sum of k summands. And I shall use the notation that if I take some subset of the indices, so 1 to k, the labels of the summands, for a vector, we denote by V sub j the projection of V to the direct sum of the summands whose index belongs to the subset j. And it's easy to see that for two vectors in the vector space V, we have that their orbit is the same if and only if for all their small projections, by small we mean that projection into an index subset whose size is bounded by the Helly dimension, the corresponding small projections have the same orbit. So as a consequence of this observation, we have, for example, that for a finite group G, we have that the separating Noether number of G is the maximum of the separating Noether numbers for representations, which are the direct sum of, at most, kappa G pairwise non-isomorphic irreducible representations. So at most kappa of G comes from this lemma above and the definition of the Helly dimension. The pairwise non-isomorphic is a consequence of this theorem of Draaisma, Kemper, and Weilau, which I mentioned before. So this was used, for example, by Barna-Scheffler to establish these explicit bounds. In fact, the results on finite abelian groups extend on diagonalizable algebraic groups. So including tori and direct products of tori with finite abelian groups. I'm not sure. Yeah. So we take now linear algebra group, which consists of diagonal matrices. So for a group element G, we call rho 1 of G, rho n of G, the diagonal elements. So this rho 1, rho n, they are functions from G into the multiplicative group of the field, and they generate the character group of this abelian group, which is a finitely generated abelian group, the direct sum of the free abelian group and some finite abelian group. And we consider an action on the polynomial algebra where the variable xi, the effect of a group element is multiplication by scalar. The scalar is given by the i's diagonal entry, of course. And in that case, it's easy to see that the algebra of invariants is spanned by G invariant monomials. And a monomial can be identified with a sequence over the character group, and it's G invariant if and only if it's a zero-sum sequence. So that's where the relation with the Davenport constant comes from. And for example, the following remark holds that for a set of monomials, it's for a set of invariant monomials, generate the algebra of invariants if and only if the corresponding zero-sum sequences generate the monoid of all zero-sum sequences over the character group. And we found, so it's interesting, so I set up the question, how can we characterize the property that the set of invariant monomials form a separating set? And it has a similar but different characterization. Yeah. Yeah, I'm afraid I'm running out of time, but just very vaguely,
You have a few more minutes. We started a couple minutes late anyway.
oh,
So you,
thanks.
you have at least 5 minutes.
Okay, thanks. So let's go back to here to, because it was maybe too fast. So yeah, so let's write B for the subset of the set of n tuples of non-negative integers alpha 1 alpha n such that rho 1 to the alpha 1 and n and so on rho n to the alpha n is 1, the trivial character. Yeah, so sometimes we think of this as a zero-sum sequence over the character groups. So rho 1 is taken alpha 1 times, rho 2 alpha 2 times, and so on. But anyway, such sequences form, so we have this additive monoid n0, the additive monoid of non-negative integer, the n-fold direct sum, so n tuples of non-negative integers with addition, and it's a submonoid there. And the elements of this monoid are in bijection with G-invariant monomials. So if S1, Sn is an element of B, then x1 to the S1 and so on, xn to the Sn is an invariant monomial, and vice versa. And now what we do is now we take some subset of the indices, and if we have a subset M of n0 to the n, then we shall write M sub j for those elements from M, all of whose components outside J are 0. So let's call it the support. If you have an n tuple of non-negative integers, the support is just those positions where we have a non-zero coordinate. And for a subset J of the full index set, write Mj for those elements whose support is contained in J. So a set of monomials is a separating set in the algebra of invariants if and only if for all subset J of the index set, the elements with that support generate ZBJ. So instead of the monoid, we take the additive subgroup generated by Bj inside Z to the n. So n0 to the n, this monoid sits inside Z to the n. And instead of B, we can take the subgroup generated by B. And instead of Bj, we can take the subgroup generated by Bj. And so instead of monoid generation, we have a group generation. We need that these monomials generated as a group. And moreover, it's not, you don't have to take all subsets of the index set, just the subsets with a bounded size. A bound is given in terms of the dimension of the group. So dimension here means that in the sense of algebraic geometry, and the rank of the torsion subgroup of the character group. Yeah. So I skip this. So how it comes up. I just mentioned a related result which appeared in a paper by Cahill, Contreras, and Hipp. They observed that for a finite abelian group, there exists a separating set of G-invariant monomials containing for each subset of the index sets of the same setup as before, with size at most kappa of G. So this comes from my result, but I observed that for each subset, you have to take only one element. So it's sufficient to take only one element for each subset of the intersect. So they were interested in this because they wanted an as small set of separating monomials as possible. So maybe I just finished to mention a few, point to some places in the literature. So for example, separating sets of multisymmetric polynomials were found by Lopatin and Reimers. So multisymmetric polynomials means that the group is the symmetric group acting on the direct sum of several copies of the standard n-dimensional representation on which the symmetric group acts by permuting the coordinates. So this comes up frequently in applications, or they describe minimal separating sets of tuples of 2 by 2 matrices for simultaneous, where the action is via simultaneous conjugation. And it's a very recent development that separating invariants of over finite fields are studied. Yeah, and finally, one interesting degree bound, separating degree bound, which I find very interesting. So it's related to matrix invariance. So let's take the general linear group GLNC acting by simultaneous conjugation on the space of k tuples of n by m matrices. And it's known that if you take products of the matrix components and their traces, these are invariants and they generate the algebra of invariants. And the degree bound is at most n squared. So this is a very tricky result of Razmislov. On the other hand, beta of CVG is at least n times n plus 1/2. So it's roughly constant times n squared. So it's between n times n plus 1/2 and n squared. And it's conjectured that it's always n times n plus 1/2. So or small n, it's always equal to that. And Derksen and Makam proved that, on the other hand, the separating degree bound for this representation is at most 4n times log 2n plus 12n minus 4, which is significantly less than n times n plus 1/2. It's less than n squared, less than constant times n squared. Yeah. So I stop here and thank you for your attention.
All right, let's thank our speaker. We can do this by clicking buttons. There's a button that says reactions. Then there's a picture of clapping. That's one thing you can do.